This video is about an interesting development in astrophysics that I've followed for some years now. It's the idea that black holes are the source of dark energy. This recently made headlines because there are tentative results suggesting that dark energy might change in time. This fits with the idea that it might be made of black holes, and it'd also determine the ultimate fate of our universe. Let's have a look. Black holes are a consequence of Einstein's theory of general relativity. They are mathematically characterized by two properties. The one is the event horizon, that's a surface from within which nothing, not even light, can escape. And in the middle, they have a singularity where everything gets squashed together to infinite density. If you fall into a black hole, you'll inevitably be dragged into the singularity, and then you can stop worrying about repaying your student loan. Dark energy is something else entirely, or so it seems. It's the name we've given to whatever it is that speeds up the expansion of the universe. Dark energy is what determines the ultimate fate of our universe, how it'll end. Will the expansion get faster and faster? Will it slow down? Is maybe even a recollapse and a new beginning possible? It all depends on this mysterious stuff, dark energy. Astrophysicists measure the change in the expansion by looking at distant galaxies. When I say distant, I don't mean they're estranged fifth cousins, I mean they are billions of light years away. We can measure how the structure and motion of these galaxies has changed with time, and that tells us how the universe expanded. And a recent measurement that from the Dark Energy Survey instrument DESI for short has delivered quite a surprise. The DESI experiment is a telescope which does a sky survey atop Kitt Peak in Arizona. It looks for baryon acoustic oscillations, patterns in galaxies that are left over from sound waves in the plasma in the early universe. Dark energy affects how those patterns change with time. So by measuring the patterns for galaxies at different ages, we can find out how dark energy changed. The group found very tentative evidence that dark energy is not constant, but getting slightly weaker. A similar finding was previously made by another experiment which looked at supernovae data. The significance of the finding is currently low, around 2.6 sigma, so maybe it'll go away with better data. However, if it's right, it means that the expansion of the universe is speeding up, but not as much as we thought, and it's getting slower. So what's causing it? This is where the black holes come in. The idea is that we've totally misunderstood what black holes do. Black holes don't just sit inside galaxies, they feel the expansion of the universe and they expand with it. And if black holes expand, their mass grows. So the mass inside the universe grows, and that can mimic dark energy. This seems to violate energy conservation, but remember that energy is just not conserved in an expanding universe. There have been some previous studies that say that the growth of these individual black holes is too small to be directly observable, and it's compatible with observations. In the new paper now, they calculate the contribution of these growing black holes to the expansion of the universe. For this, you need to know how many black holes were formed at any time in the history of the universe. It's not a steady rate. In the early universe, a lot of stars form rather suddenly once conditions allow it. Some of them later go on to form black holes. So for some while, there's a lot of black hole formation, which later slows down. This means if black holes cause dark energy, then you expect dark energy to become weaker, which is indeed what the observations suggest. In the paper, they show that the models fit the observations. They don't say this in the paper, but since black holes will eventually all evaporate entirely, I guess this would mean that dark energy will entirely disappear and the universe would recollapse. It's usually called the Big Crunch, though to me that sounds like a cereal bar. Okay, now that you know what they've done, let me tell you why I don't believe this is what's really going on. First, to make this work, you can't use normal black holes. These will just not increase in size. You need to assume black holes aren't what we think they are. They're mathematically different, have no singularity, and have internal pressure. It's an ad hoc assumption that's neither supported by mathematics nor observations. Second, that assumption doesn't make any sense because most black holes sit interested in galaxies, and galaxies simply don't expand with the universe. So what do you even want to couple them to? You may wonder now why I tell you about this if I don't believe it's true. It's because I may be wrong, and I want you to know what's going on regardless of what I think. At the very least, it'll give you something to talk about at Thanksgiving. Energy storage. I could talk about a supposed breakthrough in energy storage each day, and I'd still be talking at the end of eternal inflation. But this week I came across one that I hadn't heard of before, and it makes a lot of sense, at least to me. The major reason we need energy storage at the moment is the intermittency of solar power. Solar power is great, and it's plenty if you average over the entire globe and the entire year. We've seen prices of solar dropping dramatically and installations soaring, and this looks very promising. But we need to be able to store this energy for the dark times. Scientists have no shortage of ideas for how to do that. The best one might be hydro storage, in which you use energy to pump lots of water into a reservoir at higher altitude and then let it run back down to generate energy. And that's great, but building mountains with lakes next to them doesn't scale very well. The next most obvious energy storage is lithium-ion batteries. The trouble is that these are expensive. There are many other proposals such as hydrogen or other synthetic fuels or metals or thermal energy storage in which you heat some substance and thermally isolate it, and so on and so forth. This new method now is none of those. It relies on using sunlight to change the shapes of molecules and storing energy in that potentially for weeks. It's called molecular solar thermal energy storage. The energy from the sun falls into a molecule and changes its chemical bonds into a new configuration that has a higher energy and is metastable. This means these molecular shapes are stable for a potentially long time, but if you supply some initial energy to them, they'll decay back to the state of lower energy. You can trigger this decay with light or heat. It's quite similar to the decay you see in these chemical hand warmers, where you supply an initial trigger and the supercooled liquid releases thermal energy. This idea has a big advantage over chemical storage like hydrogen or synthetic fuels in that the molecular bonds don't need to be broken. This means that the required energy is much lower, and so it can be used with solar panels, not just with concentrated solar. At least theoretically, these materials could also outperform electrochemical batteries like lithium-ion in terms of life cycles. This is because no electrons are transported around, so the material doesn't degrade as quickly. Theoretically, this hasn't yet been borne out in reality. The entire idea is still very much at the lab stage. That's despite it not being all that new. It's been around for about 30 years. And several molecules which work have been discovered. But the trouble with those has been that they work best in the ultraviolet. This is unfortunate because most of the energy is in the visible range. Or if you want to be causally correct, I guess we should say that it's visible because it's where most of the energy is. Also, 30 years ago, people weren't all that interested in energy storage for photovoltaics, because why would you if you have all that cheap coal, right? So it's taken a long time for scientists to look into this closely. In this new paper now, a group of researchers from the University of Mainz reports they found a way to fix this problem by introducing an intermediate layer that converts the sunlight from the visible range to the ultraviolet and then stores the energy in these shape-shifting molecules. They tested about 12 cycles in a row with both sunlight and LEDs and found basically no degradation. This increases the storage efficiency by a factor of 10 above previous methods. But before you get too impressed, that's still only 5.8%. Lithium-ion batteries usually have an efficiency of 80% or so. It's like comparing my productivity on a Monday morning to a Friday afternoon. there's room for improvement. One way to increase the efficiency could be to use a molecule that doesn't release the energy in terms of thermal motion, but in terms of electricity. Now, let me be clear that this is a lab work at the very early stages, and it might go like with many of the most efficient photovoltaic cells, that they are too fragile or expensive to be used in the real world and make commercial sense. Indeed, this intermediate medium that the authors of this work use isn't cheap at all. So this isn't going to solve the photovoltaic problem anytime soon. However, if you're a fan of photovoltaics, and I know many of you are, then I think this is a development to have an eye on, because it could become an all-in-one solution for both capturing and storing sunlight. So keep calm and keep on dusting the solar panels. I recently heard Sam Altman from OpenAI say that artificial intelligence is soon going to solve all of physics. Yeah, I don't think so. Actually, things haven't been going all that well recently with AI, and I have a brief summary for you.
The main thing that I feel is important about this technology is that we are on an exponential curve, and a relatively steep one.
That was Sam Altman last year. In an essay from September titled The Intelligence Age, he wrote confidently that AI is going to get better with scale, and it's possible that we'll have superintelligence in a few thousand days. It may take longer, but I'm confident we'll get there. A few weeks ago, he concluded that soon enough, physicists will all be superfluous.
Eventually, we'll solve every problem in physics.
He's not the only one of the tech bros who's after physicists. Remember this guy, Mark Andreessen, who a few months ago wrote the Techno-Optimist Manifesto, according to which, quote, the water is warm, end quote? He has thoughts about physics too.
If you keep feeding these things enough data and enough processing cycles, they'll eventually evolve an entire internal world model, right? And they'll have like a complete understanding of physics.
This faith in the increase of AI capability is widespread. Here we have Dario Amodei, CEO of Anthropic.
From a fundamental perspective, I think it's very unlikely that the scaling laws will just stop.
And then we have, of course, Leopold Aschenbrenner, who thinks that AI will reach superhuman intelligence by 2027 or so. Reality is different. A week ago, some OpenAI employees leaked insider information to an outlet called The Information. OpenAI is currently training a new model called Orion, and while that's still in the training, according to The Information, some researchers at the company believe Orion isn't reliably better than its predecessor in handling certain tasks. Orion performs better at language tasks, but may not outperform previous models at tasks such as coding. Reuters reported that OpenAI isn't the only one running into this problem. Ilya Sutskever told Reuters recently that results from scaling up pre-training, the phase of training an AI model that uses a vast amount of unlabeled data to understand language patterns and structures, have plateaued. Bloomberg reports that Google is facing the same issue. An upcoming iteration of its Gemini software is not living up to internal expectations, according to three people with knowledge of the matter. And on X Twitter, further rumors are making rounds. Heard a leak from one of the Frontier labs. They reached an unexpected huge wall of diminishing returns. Sam Altman insists there is no wall. The reason for Altman's optimism is likely that there are several optimizations left to be done on the current large language models, which is what Aschenbrenner calls unhobbling. For example, just having these models iterate answers and thinking about them, as the newest GPT does, has been a huge improvement. Then again, if they don't scale with more data, this will only delay the problem. The only person who seems to be genuinely happy about this is Gary Marcus, who has predicted that this will come years ago. John LeCun from Meta and Bill Gates have also speculated about this. I can't say I'm happy, but I'm unsurprised. I'm also genuinely puzzled why these AI people think this will work. Part of the reason is quite plausibly that they need investors to believe it, but I've come to think it's partly because they don't understand physics. Listen to this interview with Ilya Satskeva, that's one of the guys who left OpenAI last year and then founded his own AI company.
Predicting the next token well means that you understand the underlying reality that led to the creation of that token. It's not statistics, like it is statistics, but what is statistics? In order to understand those statistics, to compress them, you need to understand what is it about the world that creates those statistics.
I find this very interesting because it's easy to see what's going wrong there. He seems to think that you can deduce the laws of an underlying reality from a higher emergent level. In the case of AI, you want to reproduce a physical model of the world, that's the underlying reality, from an emergent level, that's words and maybe videos, but in any case data that humans have produced. But we know that this generally doesn't work. You can in general not deduce the laws underlying an emergent level. Think about this for a moment. If this was so, why didn't Aristotle just deduce the standard model of particle physics sitting in a comfy chair staring at his hands? Why did we have to go and build huge particle colliders to get it done? It's because deduction only gets you so far. Then you'll need better data. In physics, it's called the decoupling of scales. I'd expect there to be a similar decoupling of scales between the details of our reality and our description of reality. Even if you take videos or images, these are extremely limited representations of the real world. To break this impasse, you need real-world data to train AI, and there isn't remotely enough. I've now had quite a few AI people telling me that data is not a problem, so they think I'm wrong and I think they're wrong, and I guess we'll see how it goes. But to me, training large language models with more data seems like going to the gym. At some point, adding more weights doesn't make you stronger. It just makes you more likely to drop something heavy on your foot. The Kessler syndrome is a chain reaction of collisions among space debris that, once it sets in, might leave orbits entirely unusable. In the past years, we've seen an increasing number of satellites breaking up and near collisions with space debris. So how close are we to the Kessler syndrome? The Kessler syndrome was conjectured in 1978 by NASA scientist Donald Kessler. Astronomers and space enthusiasts likewise have feared it ever since. Kessler said that once there is too much stuff circling in low Earth orbit, some of it will inevitably fall apart and create debris that'll uncontrollably splatter into unknown orbits. This can create a cascade in which debris gets increasingly smaller and eventually distributes around the entire globe. The issue is becoming increasingly pressing. In June, a defunct Russian satellite broke up into more than 100 pieces and forced the International Space Station to adjust course. In August, a Chinese rocket broke up upon launch, leaving behind more than 250 pieces of debris in orbit. And just 2 weeks ago, an Intelsat satellite suddenly and inexplicably lost power and seems to have broken up into at least 20 pieces, which is also a pretty good description of me on a Friday afternoon. And that's just what happened in the past couple of months. The European Space Agency estimates there are more than 100 million pieces of debris in low Earth orbit already, while most of them, about 130 million, are smaller than 1 centimeter in diameter. About 1 million is between 1 and 10 centimeters, and about 40,000 of them are larger than that. The total is more than 13,000 metric tons, about twice the weight of the Eiffel Tower. If the Kessler syndrome becomes reality, it might mean that we simply can't put any more satellites into these orbits. Most of the debris will fall down to Earth eventually, but leaving aside that this isn't great either, it'd take hundreds or even thousands of years. So just how close are we? In a paper that just appeared, scientists used a stochastic model for launches, re-entry and collisions and projected it into the future. For this, they assumed that the current launch rate of about 1,500 satellites per year remains stable. They find that runaway debris growth would begin around the year 2050. The projection sensitively depends on two factors. One is the number of pieces of debris that is created per collision, which they estimate to be between several hundred and around 1,000. The second one is the deorbit time. That's the period for how long decommissioned satellites can remain in orbit before they have to be removed, usually by burning them in the upper atmosphere. The deorbit time is currently 25 years. Reducing it to 5 years would much delay the problem and give us more time to find a way to deal with it. So how do we deal with it? Scientists and engineers have proposed various ways to deal with debris. This includes, most importantly, sweeping orbits to collect junk and then usually dumping it into the atmosphere to burn, or using lasers to nudge pieces of junk into other orbits, either to avoid collisions or, again, to force a re-entry into the atmosphere. NASA recently looked into what's the best method in terms of cost and effectiveness, and ground-based lasers came out well ahead. You may wonder why it's better to use ground-based lasers than having them in space. This is because it's easier to generate the necessary power if you're hooked onto the electric grid. By the way, I have a free weekly newsletter with some extra content. All you need to do is sign up at sabinehossenfelder.com/newsletter. Some of these efforts are already underway. For example, the project Remove Debris, which ran from 2018 to 2019. It tested technologies like nets and harpoons for capturing space junk. These tests were successful. The harpoon hit a target and the net captured a piece. However, these were not real pieces of debris, but objects that were previously deliberately placed there. One prominent project that's currently being planned is Clear Space 1, backed by the European Space Agency. If successful, it'll be the first ever mission to actually remove debris. The plan is to use robotic arms to grab and deorbit a 100-kilogram payload adapter that's been floating around in orbit since 2013. The ESA mission is scheduled for launch in 2026. And the Japanese startup X-Fusion is quite literally aiming at the sky. In cooperation with the Australian defence company Electro-Optic Systems, they are about to use a big laser to shoot small pieces of space debris out of orbit. X-Fusion, as the name suggests, actually developed their lasers to shoot at fuel pellets of hydrogen in the hope that they'll undergo nuclear fusion and create energy. However, the laser power needed to knock a small piece of junk out of the sky turns out to be lower than that needed for nuclear fusion. So if it doesn't work out with my life, I'll just call myself X-Sabine and start shooting things out of the sky. More seriously, there's a lot of commercial interest behind keeping low Earth orbits usable, so I'm quite optimistic that something will be done about it. Or maybe our children will make a hobby of collecting satellite parts. Thanks for watching. See you tomorrow.